Kinetics of particle, Newton's second law. Look at these photos. Hydraulic actuators and extending robotic arms are often analyzed using polar and cylindrical coordinates. When an object moves in a planar curved path, we can describe the motion of the center of mass of the object in terms of polar coordinates. Resolving the sum of the forces parallel to the plane into polar components and expressing the acceleration of the center of mass in terms of polar components. We can write Newton's second law in the radial and transverse direction. Okay. The sum of force along the radial direction equal the mass times the acceleration of the center of mass in terms of radial. And the sum of the force along transverse direction equal the mass times the acceleration of the center of mass in terms of transverse. AR and A theta can be evaluated by this equation. Omega is the angular velocity and alpha is the angular acceleration. Let's look at some examples. The smooth ball rotates in the horizontal plane with constant angular velocity. The unstretched length of the linear spring is R0. The color A has mass M and is released at R equal R0 with no radial velocity. Determine the radial velocity of color as a function of R. First, we have to draw free body diagram. Free body diagram of color A with the force exerted by the spring in terms of R. We have the spring, the force of a spring, and also the bar exerted a transverse force N on the color. This is the positive direction for the radial components, and this is the positive direction for transverse direction. Now we have to apply Newton's second law in the radial direction. This result is an equation for the radial components of the acceleration as a function of R. Okay. We use the chain rule to express the radial acceleration in terms of R instead of T. Separate variables and integrate it. When we integrated, we obtain the radial velocity as a function of R. As you can see, we cannot see the T in this equation. Next example. The 2 kilogram mass M is released from rest with the string horizontal. The length of the string is 0.6 meter. By using Newton's second law in terms of polar coordinates, determine the magnitude of velocity of the mass and the tension in the string when theta is 45 degrees. In this problem, first we write the Newton's second law in polar coordinate system. The sum of the force in radial direction and the sum of the force in theta direction. Also in this problem, L is constant. And therefore, the first and second derivative of L respect to the time is 0. And the equation of theta reduced to this equation. Now we have the alpha. When we integrated from alpha, we can find the angular velocity. We have to find the angular velocity when the theta is 45 degrees. We find the angular velocity is 4.81 radian per second. By this equation, we can find the velocity. Velocity equal L omega. The velocity is 2.89 meter per second. And finally, we have to find the tension in the string. Okay, from the Newton's second law in radial direction, we find this equation. We have to substitute the omega to this equation and find the tension in the string. T is 41.6 newtons. Last example. The 1 pound block is given an initial velocity 14 feet per second to the right when it is in the position theta is 0, causing it to slide up the smooth circular surface. Determine the normal force exerted on the block by the surface when theta is 60 degrees. First, we have to draw the free body diagram. We have the normal force and we have the weight. This is E theta and ER. In this direction, E theta is positive and this direction, ER is positive. Okay, we write the Newton's second law in polar coordinate system. The sum of the force in radial direction and the sum of the force in transverse direction. In this problem, R is constant. Therefore, first and the second derivative of R respect to time is 0. And then we can reduce this equation to this one. In this equation is meaning the second equation, we have alpha. We can integrate it from this equation and find the angular velocity. We have to find the angular velocity when theta is 60 degrees. The result for the omega when 60 degrees is 2.05 radian per second. And the velocity for 60 degrees is 8.20 feet per second. Thank you for watching.